So currently, in the CO2 capture and conversion communities, there are a couple of solutions that are being explored. One of these is to capture by a chemical reaction CO2 gases as they're emitted from, for example, combustion in a power plant. So one would bubble these gases or flow them through an absorber that contains a chemical that's specifically tailored to bind the CO2 and not other components of the emitted gases. And then one can take that solution and flow it through a regeneration process. So the typical chemistries that researchers are using, and actually this has already really gone to the pilot stage, so this is a maturing technology, is a chemical called an amine, or a family of chemicals called amines. These are chemicals that spontaneously absorb CO2, and they're usually implemented by diluting them in an aqueous phase, something like 30% amine in water. And then one has to take the captured CO2, incorporate it into the amine solution, and flow it through a regeneration process. And this is where the energy penalty comes in. So in the capture and storage community, capture, storage, and or sequestration communities, the goal is to take the CO2, filter it out, regenerate it into a pure form, and then take that CO2, compress it, and store it either geologically or somewhere where it will prevent its further release. The challenge is that regenerating the CO2 back to the gas phase requires significant energy input. So some estimates predict that a power plant would consume about 30% of its power output to undergo this full cycle to regenerate the CO2. So that's a big economic and energy cost for the plant, and it's difficult to incentivize the use of capture technologies if those are the metrics. So that's one approach. Another approach is to take CO2 and rather than store it geologically, and I should mention one challenge with geological storage is that it hasn't been proven on a large scale or a long-term basis. So this is sort of conceptually being explored, but we don't know how long the CO2 will really stay underground, if it's sensitive to geological events, will there be rapid release, and so on. So there are many skeptics, and I would say a high number of risks associated with this as an end product of CO2. So that has motivated researchers to look at taking the CO2 and converting it to something else. And so currently, and so I'm in the electrochemistry field, and within electrochemistry, there are two main approaches to electrochemically converting this captured and already separated CO2 to a product. The first approach is to perform what's called an aqueous reduction reaction. So what that means is you build an electrochemical cell. The CO2 is present as a dissolved reactant, and you try to reduce the CO2 to make a value-added product such as methane, so fuels, or a chemical, for example, one can think about making formic acid. The challenge there is that currently we require catalysts to drive this process to completion. And the process overall requires significant energy inputs.